Good afternoon. Thank you for joining us. It is my pleasure to be able to introduce our very own Dr. Matthew Nicol, who's a postdoctoral fellow here at the CFA in the OIR department. I had a lot of fun doing a little bit of research, background information on Matt in preparation for this. First learned that he's originally from Derry, Northern Ireland. And not everybody may know that the first extragalactic supernova, and I want to say supernova because we'll be discussing superluminous supernovae today, was actually, so where was that first one discovered? In Andromeda, it was Andromeda in the Andromeda galaxy, correct, yes. It may have been discovered by Isaac Ward, who was Irish. And I say may because it was actually Ernest Hartwig the day afterwards who published it, but then retroactively Isaac made the claim that he had seen it the night before. But two things learned. One, he was a little bit modest and afraid about making mistakes, so that's not always a good thing in science. And publish your results, right? Secondly, also, not too distant from there, the record for the world's largest telescope for the longest amount of time has the record in Ireland. Who held that record? Earl of Ross, Lord Ross, that's right. So they had it from 1845 to 1972, 72 years for the 72-inch before replaced by the Hooker at Mount Wilson. All right, aside from fun facts. Matt, you have a very impressive background. So he did his undergrad work and master's work at Oxford University, and then went to Queen's University in Belfast for his PhD. He worked with Stephen Smart on superluminous supernovae. Now, obviously, he was onto something because he was awarded the Michael Penston Prize by the Royal Astronomical Society for the best thesis. Right? And he's continued to just kind of be a pioneer in the field and has led it in his very exciting directions, to which he's going to be discussing with us today. So without further ado, please, Matt.
Okay, thank you, Dan, for that extremely kind introduction. So today I'm very excited to get to tell everybody about what I think is some of the most fun stuff that's going on right now in time domain astronomy. And really some of the progress we've made in the last few years to understanding the incredible diversity in stellar explosions. And I should say that much of this work has been done in collaboration with Ido Berger's time domain group here at the CFA, as well as with my previous colleagues in Belfast. So let's start by calibrating against a typical massive star. So as we all know, stars more than 8 times the mass of the Sun fuse nuclei in their core all the way up to iron, at which point fusion becomes endothermic when this process comes to an end. So when the core reaches the Chandrasekhar mass of 1.4 solar masses, it collapses to a neutron star and undoes all of this hard work in about 1 second. At the same time, the outer layers of the star are ejected in a supernova that probably looks something like this artist's impression. Unfortunately, the lifetime of these massive stars is only a few million years, so these planets are not inhabited. So the explosion synthesizes some radioactive elements, primarily 56 nickel, and this decays via cobalt to iron, and this powers a long-lasting light curve for weeks or months that reaches a luminosity about 1 billion times that of the Sun. And historical records of supernovae go back a long way. We've known about these things in some sense for about 2,000 years. So they occur at a rate of roughly 1 per century in a galaxy like our Milky Way. The last pseudo-naked eye supernova was supernova 1987A in the Large Magellanic Cloud. And if you get a very nearby supernova like this, you get some really beautiful data, and you don't have to rely on these artist impressions. But 1 of these per century is not really enough to do a lot of science. So for many decades, we've discovered supernovae by targeted searches of massive nearby galaxies. So the idea is that by looking at a massive galaxy with a high star formation rate, you get a large population of young and massive stars, and therefore a high supernova rate. So a typical example here is from the Lick Observatory supernova search. You can see new point sources appeared in the spiral arm of a massive nearby galaxy. But there is an inherent problem with this strategy, and that is that we're very biased towards stellar populations in massive galaxies. So in the last 10 years or so, we've been trying to remedy this through unbiased surveys, like Pan-STARRS shown here, or the Palomar Transient Factory, and others. So the idea is that instead of surveying targeted galaxies, advances in technology have allowed us to look at basically the entire sky on timescales of a few days. So the important advances are the invention of large CCDs. This is the Pan-STAR CCD that's many times the area of the full moon. Data processing capabilities, automated image subtraction to detect new point sources. And this has really been a huge transformation in transient astronomy. And these unbiased surveys have been incredibly successful at finding supernovae in very faint and otherwise anonymous host galaxies. So the image on the right is a supernova discovered by the Pan-STAR survey. And if you really squint right here on the left in the SDSS field, you can just about see a little tiny sad-looking galaxy. And in fact, these faint galaxies seem to harbor a totally unique population of supernovae that make up only 0.1% of the volumetric supernova rate. But we had no idea that these existed until recently. So the first examples of this new population started to show up at around 2005. So for a few years, there were just a couple of objects that looked very much unlike all the other known supernovae. They had very blue spectra, but they had these broad absorption features with velocities of around 10,000 kilometers per second that are sort of supernova-like velocities. But in some cases, we didn't even have redshift to know where these things were, and we've seen their galaxies are hard to detect. So these were very puzzling for a while. So this kind of changed in 2011 with this paper from Robert Quimby, where they presented 4 new objects from the Palomar Transient Factory that had secure redshift measurements from these narrow magnesium to absorption in their host galaxies. And when you line up all of these spectra in the rest frame wavelengths, you can see that these features suddenly line up, and you've got an entirely new spectroscopic class of supernovae, characterized by these oxygen-2 kind of W-shaped absorptions and very blue spectra. And these are typically found between redshifts of about 0.1 and 1. And what's really amazing about them is that at these redshifts, the implied luminosities are up to 100 times higher than conventional core collapse supernovae. And this immediately raises a range of questions. So to me, the most immediately interesting question is, what is the actual power source that allows these things to be so much more luminous than conventional core collapse supernovae? And that's really the question I'm going to focus on today. But if we understand their luminosity, this opens up a wide range of scientific potential. So obviously, the brighter they are, the further away we can find them. So if we can standardize their light curves, like in Type Ia supernovae, we could use these as distance indicators at previously inaccessible redshifts. And perhaps even detect the first generation of stars to live and die in our universe with upcoming missions like JWST, which could detect these things in principle beyond redshift 10. So this is really especially relevant right now, and also with surveys like LSST and WFIRST, that are going to detect these in much greater numbers. So we want to understand their properties as soon as possible. So as more of these things were discovered, it emerged that there were sort of 2 broad categories. One of these categories shows no hydrogen in the spectrum, and one shows strong hydrogen emission lines at a range of velocities. And so by analogy with normal supernova types, if there's no hydrogen, it's a type 1 superluminous supernova, superluminous supernova being the name for these outrageously bright supernovae, and type 2 if it does have hydrogen. So in the type 2 objects, these narrow emission lines are indicative of some low velocity material very close to the site of the explosion. In fact, the collision of the fast supernova ejecta with the slow-moving material is a plausible mechanism to power this luminosity. The power source for the type 1 objects, however, is much harder to pin down. And in fact, the type 1 objects are the only ones that show a strong preference for the kinds of dwarf galaxies I've been talking about. So this is the things that I'm going to talk about today primarily. But it's worth bearing in mind that there is a whole separate subpopulation out there. So let's be clear what we mean by dwarf galaxies in this context. So this plot shows galaxy stellar mass versus specific star formation rate. And the gray cloud here are star-forming galaxies from the Sloan Digital Sky Survey. And you can see these yellow points, ordinary core collapse supernovae, live right on top of these normal star-forming galaxies. The blue points here are the host galaxies of these type 1 superluminous supernovae. And you can see that these live in galaxies of much lower stellar mass and high specific star formation rate. And in fact, many are similar to these green points, these so-called extreme emission line galaxies, which indicate intense star formation and strong ionizing backgrounds from a population of very young and massive stars. The red points are the type 2 superluminous supernovae, and you can see that those span the whole kind of range in stellar mass here and don't have this strong bias towards the dwarf galaxies. So it is now generally thought that metallicity is the main property of these galaxies that allows you to form superluminous supernovae. So these two plots show two different diagnostics for the metallicity, parameterized in terms of oxygen abundance. And you can see that compared to other galaxy types up here, the superluminous supernovae really lie down here at the low metallicity end. So there is one potential caveat to this, in that galaxies follow a known stellar mass metallicity relation, which are these diagonal lines. So it could be that the low metallicities are a manifestation of their appearance in low mass galaxies. But I would argue that that cannot be the case, because if some other property, such as the star formation rate, was the key parameter that drove superluminous supernova formation, you would expect to find most of them in high mass galaxies where the bulk of star formation takes place. And in fact, as more and more studies have come out on this, we're converging towards a picture where superluminous supernova formation is really strongly inhibited above a metallicity of about half solar. So that's a very important clue to their progenitors. The other very interesting thing about this plot is if you look at the host of long gamma ray bursts in red, they also live down here at the same low metallicities as superluminous supernova host galaxies. And that'll be a theme I will return to later. So, as I said at the start, normal core collapse supernovae are powered by the radioactive decay of 56 nickel. And nucleosynthesis in a normal explosion synthesizes about a tenth of a solar mass of this. So the first question you might naturally ask is, if superluminous supernovae are 100 times brighter than normal supernovae, perhaps they synthesize 100 times more radioactive nickel. So to get 10 solar masses of nickel, you probably need a star of well over 100 solar masses. And these explode as hypothetical pair instability supernovae. So these have long been predicted, but never observed. But the general idea is that in this mass range, the temperature in the carbon-oxygen core gets to a point where you convert photons into electron-positron pairs. And this removes pressure support from the core, which contracts, it gets hotter, and you get a runaway thermonuclear reaction that completely unbinds the star and can produce a copious amount of heavy elements, including the requisite nickel masses. So in fact, some of the earliest observations of superluminous supernovae hinted that this scenario might well be responsible. So this plot shows the data for supernova 2007 Bi, one of the first known superluminous supernovae. And these colored curves are models of pair instability explosions. And you can see that indeed the data do seem to match this predicted slow decay. But in 2011 and 2012, we detected two new superluminous supernovae with pan-stars very shortly after explosion. So in this plot, the red points are 2007 Bi from the previous slide, and the black and the blue points are our new objects. And you can see that in sort of 50 or 60 days, they go from explosion to reach their maximum brightness. Now the colored lines here are, again, the pair instability models from the previous slide. And for these models, you can see clearly they take a lot longer than 50 days to brighten. So the problem is that their diffusion masses are so large. We've got 100 solar masses of expanding ejecta here. For photons to actually diffuse out of this material takes a very long time. And it's this photon diffusion that sets the extremely long rise to maximum brightness. So combining these observations with other arguments about the color of the spectrum, we can actually largely rule out any sensible nickel-powered model to explain these light curves. And so in fact, superluminous supernovae actually show a wide range of light curve timescales. You can see that here in this compilation of light curves, but you can perhaps see it more clearly here, where we parameterize the rise time and the decline time scale, just plot them against each other. And the objects from the previous slide are these ones circled up here. So these are the slowest time scales out of any observed superluminous supernovae. And using the light curve width as a proxy for the ejecta mass, this implies that all of the population actually have much lower masses than these so-called pair instability supernovae. Probably the light curve widths imply masses significantly less than a few tens of solar masses. So that pretty much rules out the nickel-powered model for the whole population. There's actually been a lot of debate as to whether the objects that live up here form a separate population from the ones that live down here. But when we last looked at this in 2015, there was no real statistical evidence to pick out two subpopulations. But that's something that we can look at a little bit later on. For now, I'd like to show you the spectroscopic evolution of these events. So this is now pretty well characterized. Here are the spectra of supernova 2015 BN. You'll hear that name a lot because it's now the best observed superluminous supernova in the class. So at the top here in sort of bluish, purplish colors, you can see the spectrum before maximum light while it's still brightening. And these spectra indicate really hot and ionized ejecta. The strongest lines here are oxygen 2 and iron 3, and their widths imply velocities of around 10,000 kilometers per second. So as this stuff expands pretty quickly, it cools down and recombines. And after maximum light, we see lower ionization lines of oxygen 1, iron 2, along with intermediate mass elements like calcium, silicon, and magnesium. We've got a lot of zoom-ins to different regions of the spectra here, but the main takeaway is that we don't see any evidence for hydrogen or helium in any of these kind of plots. So they do seem to be pretty stripped of their outer layers prior to explosion. And in fact, after a month or two from the time of explosion, their spectra look very similar to normal luminosity Type 1c supernovae. So the 2010 GX is an early example of this class. Here are two normal Type 1c supernovae, and you can see the broad properties of these spectra look very similar. And Type 1c supernovae we know are the normal core collapse explosions of stars that have lost their hydrogen and probably helium layers too. So this suggests that the unique blue spectra of superluminous supernovae at maximum light are really they're because of higher temperatures rather than having a significantly different composition from other stripped envelope core collapse supernovae. It's also been pointed out since then that the light curves of superluminous supernovae are pretty similar in intrinsic shape to the light curves of normal hydrogen per supernovae. A simple boost in luminosity and a single stretch in timescale can actually match the bulk of the 1C population onto the superluminous supernova population. So what that means is that the broader and brighter light curves in superluminous supernovae indicate a longer lasting power source and probably a larger ejected mass on average. So now that we're kind of up to speed on at least some of the main observed properties of superluminous supernovae, let's try to address this question of what powers the explosion. So we know we need a mechanism other than radioactive nickel decay to power the luminosity. And the broad light curves and the blue spectra indicate that this is some long-acting power source. So two main models have emerged to try and explain these properties. The first is broadly referred to as the central engine model. This could be the rotational energy of a millisecond magnetar or perhaps accretion onto a black hole. But the general idea is similar to the engine in the gamma ray burst. The difference being that instead of dumping all the energy in within a few seconds and powering a jet, this energy comes in slowly and it diffuses out after the supernova has kind of expanded to a large radius. And that gives a large luminosity rather than a large kinetic energy. The competing model, the circumstellar interaction, in this case, the supernova ejecta are expanding with an energy of around 10 to the 51 erg, a typical supernova explosion energy. And if they collide with pre-expelled material at a large radius of around 10 to the 15 centimeters, you can thermalize this kinetic energy and convert it to photons. So this probably requires a very massive and optically thick circumstellar material, probably several solar masses of stuff sitting at this radius. But in either scenario, we can well reproduce the light curves of most superluminous supernovae. So we need to look for other clues to try and break the degeneracy. I'd like to talk about one recent paper we had of a superluminous supernova that I found particularly illuminating. This supernova is Gaia 16APD, and it's one of the closest objects we've ever discovered at redshift of 0.101. So this was found by the Gaia satellite, and they described it as a blue transient in a faint galaxy. And those are exactly the kind of things that we're always on the lookout for. So looking at the optical spectra here in black, we can see that they're very typical of the class. We've got this strong blue continuum and trademark oxygen 2 absorption that then cools down over time and shows iron 2 and lower ionization lines. But the really interesting thing about this supernova, as well as being so nearby, was its very unusual ultraviolet light curves. So here are all the UV and optical light curves. You can see the optical rise and decline here, and this really steep drop off in the UV. And comparing this to a more typical superluminous supernova light curve, you can see in red we've got the R-band light curve overlaid on 2015 BN. They match very nicely around maximum light. And in blue, you can see the Gaia 16APD is 2 magnitudes brighter, but quickly drops down to the same UV flux levels. So that was very exciting and very mysterious, but is a big clue to the explosion mechanism, as I will show. So the key to understanding this came from a UV spectrum obtained from the Hubble Space Telescope by Lin Yan and collaborators in PTF. So in general for superluminous supernovae, the UV spectrum has a lot more going on compared to the optical spectrum. So the optical is relatively featureless apart from these sort of weak absorptions here. But in the UV, you've got these strong lines from carbon, titanium, silicon, and iron. And the really interesting thing about Gaia 16APD is that despite having a much steeper continuum below 3,000 angstroms compared to a more normal event, the equivalent widths of these absorption lines are actually almost identical. And we can use that fact to constrain what powers the UV emission. So let's think about how these broad absorption lines form in the context of these competing models. So if we have a engine versus CSM model, we can kind of boil this down to an internal versus an external power source. So for an internal power source, the photons are deposited here in the middle by this engine, and they have to diffuse through all of this rapidly expanding material. And that's where broad absorption lines form. In the case of an external power source, most of the energy is input at the contact discontinuity where the fast ejecta are colliding into this slow material on the outside. So in this case, the photons only have to diffuse through the slow-moving material for the most part. And since we don't see any narrow absorption lines in the spectrum, we know that the slow material is not contributing significant absorption. So we can test and discriminate between these two situations with a very simple model. So we took a well-observed superluminous supernova, IPTF 13AJG, and we performed two tests. So first, we fit the continuum and renormalized the spectrum to a hotter black body to match the UV flux and the overall SED shape in Gaia 16 APD. We rescaled to temperature of around 20,000 Kelvin and got a good match to the overall properties. And the second experiment we performed, I should say that corresponds to the situation where you've got a hotter internal power source that still has to diffuse through the same rapidly expanding cold ejecta. In the opposite case, you've got you're adding a black body because you've got the fast material is underneath the new photosphere added by the interaction. So in that situation, when you add the black body, you can still reproduce the overall kind of UV optical colors, but the absorption lines are heavily diluted relative to what we see in Gaia 16 APD. So this is very strong evidence for a hotter internal power source rather than an additional power source on top of the ejecta. So we interpreted this as strong evidence for a central engine. And there are several other lines of evidence that together also point towards this engine-powered scenario. So here I'm showing spectropolarimetry of one of the closest events, again 2015 BN. And in the top panel, you've got the flux spectra at 20 days before and 20 days after maximum light. The middle panel shows the polarization spectrum projected along the axis on which it is strongest. And the bottom panel shows the polarization spectra projected along an axis orthogonal to this. So what we see is that there's moderate polarization along one axis, but almost no polarization perpendicular to that. And that indicates that the ejecta are axisymmetric. But what's especially interesting is that the polarization signal actually increases from the early time before maximum brightness to the second epoch here. And that suggests that as the photosphere recedes, we're seeing increasingly axisymmetric material. And that's exactly what you'd expect if you've got central input with a mildly kind of collimated emission. And this is very exciting because these are really the first constraints on the geometry of the explosion. Another key recent result I'd like to talk about is the discovery of a luminous supernova accompanied by an ultra-long GRB. So in this context, by ultra-long, I mean 10,000 seconds, whereas a normal gamma ray burst lasts, a long gamma ray burst lasts for a few seconds to a few hundred seconds. And the supernova that accompanied this ultra-long GRB was also very unusual. So you can see the light curve here in blue compared to normal GRB supernova like 1998 BW and the faintest superluminous supernovae up here. And you can see that this is very much intermediate between these two groups. And the spectrum is also very unusual. It's pretty featureless, but it does show this overall strong blue continuum with some UV absorption, very much like what we see in superluminous supernovae. So let's consider the implications of this. So clearly, to have a 10 to the 4 second GRB, the GRB engine in this object has to last for a lot longer than a typical GRB engine. And we know that if superluminous supernovae are engine powered, they also have to have a long-lasting engine to stay bright after several expansion timescales. So what this suggests is that by increasing the engine timescale, you can transition from GRB supernovae to superluminous supernovae, perhaps through kind of missing link objects like this supernova 2011 KL. And this is particularly interesting given that we've already seen the similarity in the host galaxies between GRB supernovae and superluminous supernovae. Moving from the galactic scale environments to very much subgalactic environments, we've actually very recently published the first constraints on the immediate environments of these superluminous supernovae. And these immediate environments really probe the mass loss history of the progenitor stars before explosion. So in models where the luminosity comes from the supernova ejecta interacting with pre-expelled material, you typically find from modeling the optical light curves that you need mass loss rates of kind of more than 10 to the minus 2 solar masses per year, which is quite a lot of mass loss. So last year we got VLA observations of 2015 BN, this upper limit here. And if you compare our 24 gigahertz upper limit to the predicted radio light curves for a range of circumstellar densities, we can actually exclude mass loss rates of around 10 to the minus 2, right where we think the light curve needs to be powered. And we've also proposed for VLA observations in the next semester that would fall here and would rule out models with around 10 to the minus 1 solar masses per year. So that'll be extremely constraining for any kind of circumstellar interaction model to fit the optical light curve of 15 BN. We've also just submitted a paper, which may come out today or tomorrow, led by Raffaella Margutti, analyzing all of the X-ray data for superluminous supernovae from Chandra, XMM, and Swift. And for the nearest events, we have some pretty constraining data, one non-detection and a deep upper limit and an actual detection, of the two nearest events. So for 2015 BN, there's a non-detection in X-rays that constrains the mass loss rate to a similar degree to our radio data. We can rule out mass loss rates of around 10 to the minus 2 solar masses per year. And you can also see that that is comparable to the other supernovae type 2N that we know are interacting with dense mass loss. For PTF12 DAM, the limits are even more constraining. So this one we actually did detect in X-rays. And the X-ray flux that we measure suggests a mass loss rate of less than 10 to the minus 5 solar masses per year. And that is nowhere near enough to power the light curve through interaction, and is also very similar to the mass loss rates around normal type 1c supernovae, which we know are the explosions of compact stars in low density environments. So I've just thrown a lot of reasons at you why most of the community are now converging towards a view where superluminous supernovae are powered by some kind of central engine. And now I'd like to see how this idea holds up in the context of the best observed event in the class, and therefore hopefully the most constraining. So 2015 BN that I mentioned before was discovered by Pan-STARRS and independently by the Catalina Sky Survey. And we follow this up with spectra every few days and photometry from the UV through to the near infrared to give these beautiful data sets that you see here. This was also the radio limit we saw, the spectropolarimetry. So we've learned a lot of science just from studying this one supernova. And I spent a lot of time working on this over the last couple of years. But there's one aspect in particular that I want to talk about today. And that is the very late time observations. So a supernova is fundamentally an expanding ball of gas that is very hot and therefore very ionized. And therefore much of the physics is obscured behind an electron scattering photosphere. But as the ejecta expands and cools down, this material recombines, the density drops, and this photosphere recedes in mass coordinate deeper into the ejecta. So the idea is that if you watch it for long enough, eventually you can see all the way through to the center of the nebula. Unfortunately, this takes several hundred days in the case of superluminous supernovae. And at the typical redshifts where we find these events, you can't follow them for several hundred days. They just fade below detection limits. But luckily for us, 2015 BN, as well as being one of the most nearby objects, it was also one of the brightest and one of the slowest to fade away. So we were able to follow this for almost 500 days just from the ground. We've got some scheduled HST time to pick this up again from space at around 800 days after explosion. So you can see our very long-lasting light curve here. But more importantly, if we track the evolution of the black body radius, you can see that after around 100 days from explosion, it turns over. And by 300 or 400 days, it's actually receded almost all the way back down to the center of the explosion. So we can see at this point kind of right into the heart of the beast here. So what does it look like? In the left panel, we've got the spectroscopic evolution from very early times all the way through to our final spectrum 400 days after maximum brightness. And you can see that the blue continuum gradually disappears and these strong emission lines pop out instead. So the strongest lines are identified as being mostly oxygen as well as calcium and magnesium. And the oxygen lines in particular are very useful for constraining some of the physical properties. So taking the ratios between forbidden oxygen lines implies a temperature of around 5,000 Kelvin, which suggests there's some ongoing heating even at this very late phase. And from the luminosity in the strongest oxygen line alone, we can infer an oxygen mass of around 10 solar masses, which should make up the bulk of the explosion. And this was subsequently confirmed by detailed nebular spectral modeling from Anders Yerkstrand and others. Combining the derived mass of around 10 solar masses with the observed line widths, we infer a kinetic energy of around 5 times 10 to the 51 ergs, which is several times higher than in a normal supernova explosion. I think the most interesting line here is the narrow oxygen 1 line, a permitted recombination line at 77, 74 angstroms. The reason this is interesting is that this requires a high density and is clearly at a much lower velocity than the other lines. And this is indicative of a high density inner shell in the ejecta, which is actually one of the hallmarks of a central overpressure that kind of sweeps up this innermost material. And this line is not seen in normal type 1c supernovae. And so finally, the best thing about it is that if we overplot the spectrum of hyperenergetic supernovae such as those that accompany gamma ray bursts, like 1998 BW, we get a near perfect match, which indicates the interior structures of superluminous supernovae really closely match the interior structures of GRB supernovae. And in some ways, this is kind of a smoking gun for a central engine model. So we were very excited about this. And for the reasons I've just described, I'm now personally pretty convinced that superluminous supernova light curves are indeed powered by a central engine. So I think it's time to be more explicit about what this engine actually is. So we know that core collapse supernovae form compact objects, either neutron stars or black holes. In the case of gamma ray bursts, the most popular model is that you form a rapidly rotating black hole that supports an accretion disk, and this drives a jet into the ejecta. So that's shown here by this rather old but still very beautiful figure. However, it's equally possible that GRBs could be powered by a rapidly rotating neutron star with a strong magnetic field to extract this rotational energy. So a maximally rotating neutron star has about 10 to the 52 erg of energy available in rotation, and that's actually comparable to the brightest observed GRB supernovae. For superluminous supernovae, however, we need a longer-lived engine. As I mentioned before, the energy comes out days or weeks after explosion rather than seconds. So in the case of a black hole, the time scale for this engine is set by the fallback time, which for a hydrogen per star is only a few minutes, which is not long enough to power the light curves that we see. So for that reason, it seems that the neutron star scenario is much more conducive to forming superluminous supernovae, because it can give a wide range of timescales depending on the magnetic field value. So let's talk about magnetars. When I typed this word into Google to find a nice artist impression, I got this nice sentence: a magnetar is either a guitar made of magnets, the son of Magneto, a Decepticon, or a giant star. And I like that because they're all equally wrong. In astronomy, it means a magnetized neutron star, very much a compact star. So known galactic magnetars can have a B field of up to around 10 to the 15 Gauss, but they are slow rotators, which is important because if the initial spin period is milliseconds rather than seconds in the case of galactic magnetars, the rotational energy can significantly influence the dynamics and the luminosity of the explosion. So it's thought that the magnetar should emit its rotational energy as a magnetic dipole with a spin-down power and a timescale that depend on the spin value and the magnetic field. To match the luminosities at peak in a superluminous supernova, we require close to maximal rotation, a few milliseconds, and a B field of around 10 to the 13 to 10 to the 14 Gauss to match the timescales. But what's very nice is that recent simulations show the magneto-rotational instability in a rapidly rotating proto-neutron star can actually amplify a relatively weak seed field up to magnetar strength values. So here's 3 snapshots from a simulation showing the increase in the magnetic flux density with time. I think the yellow means 10 to the 15 Gauss, as far as I recall. But what's really nice about this is that if we have the rotation at the moment of neutron star formation, we kind of get the magnetic field for free. So sometimes when I give talks like this, people will ask me if there's any hope of actually seeing these magnetars themselves to really prove that superluminous supernovae are powered by magnetars. And usually I'm very pessimistic and say basically no, they're much too far away at redshift of point a few. But today I want to be much more provocative and say that actually we may have seen these already in the form of fast radio bursts. So these are another recently discovered and very exciting class of transient, which were discovered in archival data from the Parkes Radio Telescope in Australia. So these are bright flares, roughly Janskys, that last for a few milliseconds, and they're characterized by this large dispersion measure, this quadratic sweep in arrival time versus frequency. And the amount of dispersion suggests a long path through some dispersive medium, which hinted at an extragalactic origin, but they proved very difficult to localize. However, their brightness suggests a coherent emission process, And combining that with a short timescale over which they occur suggests that they come from a compact object. And for this reason, models involving neutron stars and magnetars have been very popular. However, I should note that we've never seen an FRB from a magnetar in our own Milky Way. So as Ido discussed at lunchtime, there was a huge boost for FRB science this year with the discovery that one FRB, 121102, actually repeats. So this was found by Arecibo, and the higher sensitivity of this telescope compared to Parkes allowed them to detect multiple bursts from the same source, which had the same dispersion measure but a range of flux values. But the beauty of having a repeating source is that that means eventually you can find it with an interferometer, and then you actually know where it is. So this was finally localized this year after 90 hours of follow-up with the very large array. And this was well worth the effort because the result was very surprising. So not only did they find that it is indeed extragalactic, the host galaxy was found to be a dwarf galaxy almost identical to the hosts of superluminous supernovae. So this Gemini image shows this little smudgy compact galaxy at a redshift of 0.19. And if we look at, for example, line ratio diagnostics, the host galaxy of the repeating FRB lives here in this obscure kind of corner, exactly where we find type 1 superluminous supernovae, and very far away from where the bulk of star formation occurs. So that was very exciting, and it's prompted, as Ido described, Brian Metzger, Ido, and others to propose that FRBs are not only flares from magnetic neutron stars. These are very specifically flares from the millisecond magnetar remnants of recent superluminous supernovae and possibly long gamma ray bursts. This could also explain the existence of a quiescent radio source spatially coincident with the FRBs, either as Ido mentioned, an energetic pulsar wind nebula or supernova shock wave interacting with an external medium. So this is very exciting because if we can robustly establish that there is a link between superluminous supernovae and FRBs, we'll simultaneously solve for the origins of both classes, these millisecond magnetars, which would be obviously a huge result for transient science. But actually, there's one test we can do right now with no additional observations to try and test this scenario, and that is the following. If these classes are linked, there must be a link between the superluminous supernova rate and the FRB rate. So we recently posted a paper on the archive to explore this link, and now I would like to take you through some of those calculations. So for any rate comparison, we have to start by defining a volume. So we take the dispersion measure of known fast radio bursts. There's about, I think, 18 published or something like that. And in each case, we remove the Milky Way contribution to the dispersion measure, and we assume the host galaxy is similar to the host of the repeater. You can then take the remaining intergalactic component of the dispersion and convert that to a redshift using known relations. So what we find was that actually the sensitivity to FRB seems to drop pretty sharply above a redshift of about 1/2. And that's currently unexplained, whether that's an observational bias or there's something physically stopping us from finding higher redshift ones, we're not sure. But we do seem to be complete up to a redshift of around 0.5. So we took that as our fiducial search volume. So within this volume, we then calculated the magnetar birth rate, assuming various progenitor channels. The example here is for superluminous supernovae. There are multiple estimates for the superluminous supernova rate at various redshifts, but it's been shown that these can be roughly normalized to the cosmic star formation rate, as you might expect. So integrating this curve up to redshift of 0.5 suggests that there are a few times 10 superluminous supernovae per gigaparsec cubed per year, which is not very many. But if we do a similar calculation for long and short gamma ray bursts using the rates from Swift, this goes up by a factor of a few. So I should point out that short gamma ray bursts are not formed in core collapse supernovae. These are thought to be from binary neutron star mergers. But it's been suggested that a few percent of those might also leave behind stable millisecond magnetars rather than black holes. So we do include those in our rate estimates. So if GRBs also contribute to the magnetar formation rate, this goes up by a factor of a few to kind of a few tens or hundreds per gigaparsec cubed per year for an overall plausible millisecond magnetar birth rate. Also, for the Milky Way type magnetars, the slow rotators, those seem to be much more common. Those appear to be born in about 10% of all supernovae. So their birth rate is around 10 to the 4 per gigaparsec cubed per year. It totally dominates the formation rate. But again, those we think are slow rotators compared to the millisecond magnetars here. So we then did something similar for fast radio bursts. The all-sky rate has been estimated as a few thousand per day with a flux above 1 Jansky. And we can convert this into a volumetric rate if we can construct a luminosity function. So what we did was to assume that these are all similar to the repeater. And then we constructed the cumulative luminosity distribution of bursts from that repeater. And we fit this with a Power law with an index of around minus 0.7. So very encouragingly, Vikram Ravi, who was here last week, has done a similar analysis for the full Parkes FRB sample, which is many different FRBs from different sources rather than repeating FRBs from the same source, but finds the same Power law index. So with this luminosity function, we can get the all-sky rate by integrating over redshift the product of bursts above 1 Jansky in the observer frame, the volume density of repeater sources, and several factors to account for beaming, time dilation, and star formation rate. And what we find is that the source density is around 10 to the 4 repeating FRB sources per gigaparsec cubed. And that number is the product of the repeater birth rate and the lifetime for which they live as FRB repeaters. So with that, we can do some comparisons. And I do apologize for putting a table in a talk, but we do want to look at some limiting cases from this list of numbers here. So first of all, if FRBs are not repeaters and simply cataclysmic events, to match the observed rates, you actually need to have an FRB rate similar to the core collapse supernova rate, which seems quite unrealistic, especially when we consider that there's no reason that such a common event would favor dwarf galaxies like the repeating FRB that we've seen. If we instead assume that FRBs come from normal slow rotating magnetars from normal core collapse supernovae, the implied lifetime, simply from equating these two rates, is less than a year. So that's bad for two reasons. So firstly, the repeater has been observed to burst for more than 4 years. So observationally, that's pretty challenging. There's also a theoretical reason that that does not work out, in that it takes much more than a year for the supernova ejecta to become optically thin at the gigahertz frequencies at which FRBs are emitted. So it seems like only a small minority of core collapse supernovae can leave behind FRB sources. So if that small minority are the millisecond magnetars from superluminous supernovae and GRBs, the implied lifetime works out to be a few tens to hundreds of years. So first of all, good news, it's longer than 4 years. But secondly, it also perfectly matches the theoretical predictions from Brian Metzger and Ito, who set the theoretical lower limit on the FRB lifetime from the time to become optically thin in the ejecta, which is a few decades, and an upper limit from the time it takes the FRB source to radiate away all its energy in FRBs. And it runs out of magnetic energy in around a few hundred years. So a theoretical range is tens to hundreds of years. The rate estimates give us a range of tens to hundreds of years. So if we believe that FRBs come from the millisecond magnetar remnants of superluminous supernovae, this actually comes together as a really nice, consistent picture. These birth rates are really well matched. But we have to remember that this entire analysis, this proposed FRB superluminous supernova connection, is still based on a single localization in a single dwarf galaxy. So the real test of this scenario will come with future localizations and better sampling of the host galaxy statistics. So as a first step, we performed some Monte Carlo simulations of future FRB localizations for various different progenitor channels that could lead to magnetar birth. So this figure shows the probability of finding a galaxy more than about 0.5 L star in luminosity, or B band magnitude of minus 20, as a function of the number of FRBs localized. So if you have any channel that's proportional to stellar mass, you expect to find a massive galaxy within 5 localizations at 95% confidence. So it does not take that many localizations exclusively in dwarf galaxies to rule out a lot of these other channels. Similarly, for short GRBs or any kind of compact object mergers, you expect that those should also occur in elliptical galaxies. So finding one FRB in an elliptical galaxy, never finding an FRB in an elliptical galaxy can help to rule out those channels. So overall, it seems like you only need kind of 10 localizations to exclude a lot of channels and only leave behind sort of superluminous supernovae and maybe long gamma ray bursts. So it seems like in the near future we could plausibly constrain the progenitors of FRBs just from the host demographics. But we also have some proposals to do these tests more directly. We're going to look with, well, if we get a word at a time, we will look with the VLA, with ALMA, and with Arecibo at the sites of recent superluminous supernovae to look for quiescent radio sources and perhaps even the FRBs themselves. But any predictions for how these magnetars can power the FRBs are dependent on understanding the superluminous supernova parameter space. And even for the superluminous supernovae themselves, much of the diversity remains relatively unexplored. So what we want to do right now is to try and pin down where these superluminous events really live in parameter space. What are the combinations of spin, magnetic field, ejected mass that actually result in these explosions? So typically, these properties are inferred via model fitting the volumetric light curves. But this results in many systematic uncertainties. So there's difficulty in deriving a volumetric light curve from what's normally fairly limited optical data. And many different groups implement slightly different versions of this magnetar model in different codes. So we want to try and fix this. So to do so, we've been completing the most intense sort of census and modeling effort of all the superluminous supernova properties undertaken to date. And to do this, we've written an all-new multi-purpose code, an open source code to do Bayesian light curve fitting to any supernova or transient of your choosing. So kind of overkill for this problem, but hopefully widely applicable for a lot of transient astronomy. So we call this code MOSFIT. It's the modular open source fitter for transients. And code development was led by James Guillochon here at the ITC. And he also made this beautiful logo. And I've been sort of implementing this superluminous supernova magnetar model and benchmarking the code against all available observations. And one really nice thing is that this interacts directly with the Open Supernova catalog, making it very simple to kind of plug and play with your model against all the data that's already out there. But today I would like to show, actually for the first time, some of the results of our population study, hopefully with papers due out in a month or two, along with the public release of the code. So here are some example fits. So each color is a different wavelength filter, and all of these lines are the 100 realizations of the Markov chain Monte Carlo fitting procedure. So in the top row are 3 superluminous supernovae with really nice, well-sampled light curves in a range of filters. And you can see that we do a really nice job of fitting both the broad structure and also the color differences between all of these objects. So that's very nice. But what makes me even happier is how well we can fit the objects that have very limited data. So for example, you could have very poor signal to noise. You could have just kind of only 2 random filters at high redshift. And in the most pathological case, you might have no simultaneous coverage at different wavelengths. And this would make it almost impossible to construct a reliable volumetric light curve and model these the traditional way. But with MOSFET, it's pretty straightforward to sort of build an SED and to try and fit the observational data directly. So with this method, we've increased the sample of superluminous supernovae to 35 objects, which are all the objects in the literature with published light curves. And we derive posteriors like these for every object. So the model constrains key physical parameters. I don't know how well you can see this. Spin period, magnetic field, ejected mass, kinetic energy. These are the most interesting ones. We want to compare, first of all, the case of 2015 BN, because it's a nice benchmarking case since we have independent constraints on some of these properties from the nebular spectrum that I showed earlier. So in this case, we find a spin period of 2 milliseconds, a B field of a few times 10 to the 13 Gauss, and an ejected mass of around 12 solar masses, with a kinetic energy of 3 or 4 times 10 to the 51 erg. And if you cast your mind right back, that's pretty much spot on what we derived from the nebular spectrum. So that's very reassuring that we converge in the same numbers from completely different methods of constraining these parameters. We also find a large opacity and a low extinction, both of which are consistent with what we expect for superluminous supernovae, given the ionization in the ejecta and what we know about their host galaxies. Here is a similar plot, but here is the summed posteriors for all 35 objects in the sample to really find exactly where these things live in parameter space. And we find that their spins are close to maximal. The median is 2.4 milliseconds, which is within a factor of a few of the neutron star breakup velocity. Typical B field of about 10 to the 14 Gauss. And the ejecta mass spans sort of 2 to 11 solar masses at 1 sigma. The kinetic energy is around a few times 10 to the 51 erg, giving an average velocity of about 10,000 kilometers per second. So one important reminder here, even if I have not convinced you that these things are powered by magnetars, you can still take this model with these posteriors and reproduce the entire kind of observed distribution of superluminous supernova light curves. And that allows us to do things like predict what they will look like to future surveys such as LSST or WFIRST. And it's very important to start doing this as soon as possible. These future surveys will discover many, many more of these, but they will be very hard to pick out of the data stream. It's set to be an overwhelmingly large data stream. But by modeling the light curves for these surveys from realistic priors, taking our posteriors as priors for these surveys, we can try and learn how to find these early without spectroscopy. So that's very exciting. So I mentioned at the start that observationally there seems to be a subset of superluminous supernovae with very broad light curves. And some people term these slow evolving or long duration superluminous supernovae. But I don't think it's been shown yet that these really are a separate class. So previously with 24 objects, the statistics were consistent with a single population. But I thought it would be fun to look back at this question now with a larger sample and a much better handle on the parameters that probably underlie the light curve shapes. So what we did was to look to see if any of these parameters sort of separate out nicely into two populations. So here are the same posteriors before, just kind of zoomed in on the interesting ones. And the black histograms are the fast objects here. The blue are the slow objects up here. And you can see that the slow objects kind of favor a lower B field and a higher ejected mass, and maybe a lower velocity. But there's no obvious bimodality here. It's not that one parameter kind of separates out cleanly and gives two populations. And in fact, looking at the spin period and the kinetic energy, the two posteriors are almost identical. So I think that that is evidence that all of these diverse objects come from a single population. And really, this magnetar model can generate a very surprisingly large range of light curves. The fact that these may all be one population, I think, is also consistent with the fact that the spectra are pretty similar between everything on this plot. The final thing I'd like to show from these new models is the distribution of the kinetic energy. So spectroscopically, we've seen that these type 1 superluminous supernovae resemble both type 1c supernovae and hyperenergetic broadline type 1cs associated with gamma ray bursts. They're also connected to these objects from their nebular spectrum and the host galaxies. So here's the kinetic energy versus the ejected mass for superluminous supernovae. You don't have to worry about what these different colors mean. Compared to the 1bc's in these squares, and the broadline 1c's are the gray diamonds. And what we find is that the superluminous supernovae sit very nicely in between these two groups of objects to kind of span this gap. And that's nice because that's actually exactly what you would expect if the engine in the superluminous supernova contributes some kinetic energy, but not as much as in the GRB supernovae. And we know it has to use some of this as luminosity rather than kinetic energy, so that holds together fairly consistently. So I think this plot also supports this connection that superluminous supernovae and GRBs are sort of different manifestations of engine-powered supernovae, just kind of with different timescales. So before I finish, there's just three other kind of interesting, outstanding questions I'd like to highlight. So I think these will drive a lot of the superluminous supernova science over the next few years. So firstly is the recent discovery that some of these supposedly hydrogen-poor objects actually show these strong hydrogen emission lines in H-alpha at several hundred days after explosion. So what this probably means is that the expanding material at some point collides with a shell of hydrogen-rich stuff at sort of a few thousand AU. And that should prove to be very constraining for actually determining the mechanism by which the progenitor star loses their hydrogen envelopes before explosion. The second thing is the discovery that some of these objects, at least some of these objects, have this short initial peak here before the main rise to maximum light. So this peak is pretty bright, but only lasts for a few days, which has made it very difficult to detect. It sort of falls through the gaps in a lot of surveys. So it may actually be common in these objects if we were better at finding it. The temperature during this phase can reach up to 30,000 Kelvin and seems to require a fairly large radius to get the luminosity. So this could indicate some kind of engine-driven shock breakout or even a weak jet possibly breaking out of the expanding ejecta. So hopefully with future surveys like LSST, it'll be very good at finding this bump and also getting multicolor data to model the temperature evolution. And finally, there's the exciting possibility that at least that some superluminous supernova light curves can be standardized, like Type Ia supernovae, in some kind of width-luminosity relationship. So based on a small number of objects, Inster and Smart proposed that you can fit a pretty strong, actually, width-luminosity relationship here. But this really needs to be tested in the context of the much larger sample that we have now. And one thing I want to do is to look and see if we can reproduce a width-luminosity relationship from our posteriors for the Magnetar fits. So I think that could be exciting, because if these are standardizable, that would allow supernova cosmology up to redshift 10. These things are not only very bright, they're also extremely blue, which makes them perfect for finding high redshift. So that brings me to the end. So to conclude, the brightest explosions in our universe seem to be confined to the faintest galaxies, and also seem to be linked to gamma ray bursts through those host galaxies, through nebular spectra, and even one observed ultra-long GRB. Observations in theory are converging on a picture now where superluminous supernovae seem to be powered by continuous energy injection from a central engine, which seems very likely to be a millisecond magnetar. And that they are a diverse family, but our Bayesian modeling seems to confine the parameter space and indicate that the ejecta mass and kinetic energy are higher on average than other stripped envelope supernovae. And most remarkably of all, I think, the two most surprising new transients of the last decade, superluminous supernovae and fast radio bursts, appear to originate in similar anonymous galaxies and may even be linked through this magnetar birth. The rates, the host galaxy demographics, and the repetition times of FRBs will soon tell us whether this is the case. I'll finish there. Thank you very much.
Very much. All right. Ready to open the floor to questions. Yes.
In your fit using MOSFET, did you find some of the magnetars? What range of magnetic fields do you find?
I can go back and find that plot. Too far. Okay. So the B field, if I kind of squint, it's this one. So it kind of spans from around 10 to the minus 10 to the 13 up to a few times 10 to the 14, guys.
13
So,
14.
yeah, maybe a few times 10 to the 14. The median is roughly 10 to the 14. So it seems to be maybe a little bit less than the B fields inferred for GRB supernovae, for example, if those are to be powered by magnetars.
Yeah, some of them, we have a model of FRB radiation mechanism. Some of the at 10 to the 13 probably not able to produce FRBs. Only those above probably 10 to the 14 Gauss.
Oh, really?
Yeah.
So that would suggest that only some.
If only a small fraction of them is about 10 to the 14.
Yeah, no, it's a reasonable fraction. You know, the median is about 10 to the 14, so perhaps half of them are in the range that works for your model. But,
yeah.
Well, it's really impressive to put all of this together. I have a basic question which goes back to your point early on about low metallicity. So, it seems pretty convincing that, this population is limited to the range of lower metallicity, and the central engine argument looks very good, and the magnetar argument is really coming along, looking much better all the time. So how do these link up, though, the low metallicity and this power source? Do you see what that fundamental link is?
I think that's the biggest thing missing right now from kind of the theoretical literature on these. No one's really proposed beyond a hand-wavy level how the low metallicity leads to engine formation. It must be linked in some way to, you need a rapidly rotating core at the point of collapse. So by limiting the metallicity, perhaps you reduce angular momentum loss in winds or something like that. But you've got to lose the hydrogen layer somehow, so there seems to be a contradiction in there. You've got to lose the hydrogen layer without losing too much momentum. So no one's really shown how low metallicity allows you to do that.
Yeah, that would be a key. If we had that, then I think, we'd really, feel we had a physical handle on what's going on here.
I mean, I think you can form more massive stars. The IMF might be different in these low metallicity galaxies, but how that actually helps to produce the stars that give you these is very unclear.
Yeah, I was going to put the spotlight not on you, but on the community. I just came from a workshop where they were complaining about the core having such rapid rotation at the time of collapse, unless you had a binary companion. So,
yeah.
you want a strong magnetic field and you want things rotating at that speed. It's very difficult to do it on its own.
Yeah, my opinion for sure is that these are binaries in some way, but how you actually test that is so difficult.
Well, some people claim that all massive stars are binaries.
Well, observational evidence
Yeah.
seems to suggest that a good fraction, about 70% of, say, for instance, O stars will have some kind of a binary that they'll interact with at some time, yeah.
One thing to remember is that these things are so rare, it can be very difficult to form them, and that's still okay because you don't have to form very many of them. So,
We still need a path.
yes,
That's right.
but as long as it works occasionally, then that's fine. Which does not help us at all, but is observationally that's a fact.
Very good. Yes?
So when you fit the photometry light curves with your model, you get all these estimates. Since your model is an SED, can't you use those estimates for light curve fit to predict what the spectrum would be at any given phase? And have you compared that to like an observed spectrum, and do they match up?
So these are very simple spectra that we're using. The SED is just assumed to be a black body plus some UV absorption based on the observed UV absorption. The reason we can do that for these is because the spectra are relatively very featureless compared to other supernova types. You've got nothing like a strong H alpha in a type 2 or a strong silicon in a 1A. So really all we're confirming is that a black body gives you the right colors for these things. Lines on top of that are a small perturbation. So we could make this better by using the observed spectra to construct the SED, but it's unlikely to make any difference to the posteriors that we derive. It would be a very small perturbation on top of this.
Yes?
I thought you said that most of the ejected mass is oxygen, and I'm wondering what fraction that is and where that comes from.
So there are more detailed models of the nebular spectrum that people have constructed, from first principles, and they fit these reasonably well. I cannot give you a number for the fraction. I feel like something like 70% is about right. I think it's not unusual for a hydrogen per star. And once you've lost the hydrogen in the helium layers, oxygen is the next most abundant thing. So I think it's sort of a similar number to other kind of type 1C supernovae.
I'll just comment there, done a little bit of this with the 1C. There are a lot of assumptions that go into how you make that mass estimate, in the sense of the transfer is difficult at that stage, and you have to assume how the mass is distributed. And as you mentioned, it was outstanding. It is unexpected that some of these cases they ran into some hydrogen material after explosion. So the story's still growing on types of stars leading up immediately before they get the explosion.
Absolutely.
Yeah. Yes?
If the neutron star loses its magnetic energy fairly quickly, would you expect to see a bunch of FRBs that had large dispersion measure from the expanding supernova?
So I think the difference between the FRBs and the supernova is that the supernova is powered by the rotational energy, and the B field changes very little over the lifetime of the supernova, and then it decays very gradually through FRBs over a much longer time scale. So you probably wouldn't see it observing the supernova. In the FRBs, there are some constraints that Ido mentioned at lunchtime today, that the dispersion measure seems to not change very much as a function of time for the repeater, which actually puts some constraints on the sort of how much the ejecta are evolving with time. I mean, that's one reason we think they have to be at least a few decades old.
Okay, I think we'll end it there. Let's thank our speaker.